Hello physicists and welcome. In this session we'll be covering momentum part 1. Our learning objectives are: I can calculate the momentum of each object in a system, and I can determine the momentum, mass, or velocity of an object given two of those values. Let's get started. In this first clip, we'll take a look at two bowling balls being thrown at different speeds. The bowling balls are roughly the same size. The small girl on the right rolled her ball down, the man on the left rolled his down, and we'll see that there's a difference in the effect once it gets down to the end of the lane. If you were a bowling pin, which would you fear more, the one being rolled by the girl or by the man on the left? Let's take a look at a couple of situations where an object is traveling the same speed, but we're going to look at different size objects. In this initial throw, a ball is being thrown about 50 miles an hour, and except for a slight sting in the hand, could be caught easily by a person here. This is from the movie A League of Her Own.
Watch this.
In this clip, we're seeing a downhill racer from a recent Tour de France going about 50 miles an hour, where he loses control and ends up hitting a wall and then sliding over that wall. Think about the wall. The wall hardly moved at all. We have the same speed, but think about what ends up happening here. Our rider was slightly injured, but you can see here is able to get back on the bike and continue on the rest of this race.
And all set to rock. Terrific. Back into the race and still ahead of the peloton, by the way, at the moment.
We'll look at another situation here. Same speed, about 50 miles an hour. We'll have a car running into a barrier. And then you can think about, hey, would you want to be standing in front of that car, in front of the bike and rider, or in front of the baseball? What's different about this situation? All three of the objects that we've looked at so far are all traveling about 50 miles an hour. Let's go and pick it up a bit now. Now we have a truck traveling about 50 miles an hour into a barrier. We get another view of this. Again, traveling at about 50 miles an hour. Again, think about which of these objects would you want to be standing in front of. All are traveling at about 50 miles an hour. In our last one, I'll let it kind of run just because it's a fairly dramatic footage here. Just a heads up, no one was, no one was hurt in this episode. Our train was traveling at about 50 miles an hour as it struck the truck that was stopped on the tracks. So watch carefully at the cab of the truck. You'll see the driver steps out of the cab and we'll start walking away. We'll get another view from the other side in just a few moments. I'm not sure why the gates drop on both sides of the track. So the cab is separated from the rest of the truck. The train is still continuing it on at about 50 miles an hour. And fortunately, our driver is able to step out of the cab. For our examples, you can see that this quantity momentum that we're talking about is a product of both the mass of an object and its velocity. Let's go and define these terms. Hey, the mass is the amount of material there. It's related to its weight. On Earth, we can't really tell the difference between the two, but does not change with the location. The unit of mass that we'll be using in this class is the kilogram. Objects have the same mass whether they're on Earth, the moon, or in outer space. Where their weight may change, the mass doesn't. If I were to count up all the atoms inside there, they're the same in all those places. But the weight would change, but the mass stays the same. Let's look at velocity. Velocity, it's the rate that the position is changing with direction. The unit is the meter per second, and we also have to define a direction as well. Because it is a value with a direction, it's known as a vector quantity. So it's a quantity with magnitude and direction. Other units that we've used for speed or velocity: miles per hour, feet per minute. So we can just think of velocity as a speed with direction. Now let's do some sample calculations here. Hey, the unit used for momentum is P. It's short for progress, and it has these odd units of the kilogram meter per second. There's no shorter name than that, although sometimes in class we will call it the mo, short for momentum. Let's do some practice calculations. Okay. Hey, we have a young soccer player has kicked the ball, and we'll say this ball has a mass of 0.4 kilograms, and it's kicked with a velocity of 15 meters per second to the right. Let's go and figure out what that momentum is. Momentum. I'll put these little hats over there indicating it's a vector. Is mass times velocity. So 0.4 kilograms times 15 meters per second equals 6 kilogram meters per second to the right. I guess I'll put that up here. For our soccer ball, if we were to define a coordinate system and we called to the right the positive direction, then we could say it has a momentum of a positive 6 kilogram meters per second. Let's look at another example. Hey, we got a roadrunner. Our roadrunner, you can see this case is running to the left, so we're going to call that the negative direction. Hey, taking a look at things, it looks like the mass of a large roadrunner is about 1.5 kilograms. Unlike the cartoon, the maximum velocity of a roadrunner is about 20 to 25 miles an hour. We'll say, let's see, if you want a good rule of thumb, if we can take our speed in miles per hour, which makes more sense to me, but we want to turn it into meters per second, which is what we'll use in scientific notation, we would say that this has a velocity 20 to 25 miles per hour is about 12 meters per second. So the momentum of our roadrunner is, I'll put a note about this being left, or I could put another way of saying it is the minus sign, 1.5 kilograms times negative 12 meters per second. I get a momentum for our roadrunner of minus 18 kilogram meters per second. And remember that negative sign indicates that our roadrunner is moving to the left. I want to compare the momentum of two objects. We'll do some more calculations. I'm going to look at the momentum of a paintball pellet and a watermelon being thrown. All right, so let's take a look at this. Our paintball pellet. Let's see. When I checked out, it looks like paintball guns shoot their pellets at around 160 miles per hour, about 80 meters per second. And the mass of that would be, let's see, 0.005 kilograms. It's about 5 grams, about the same as a penny. So the momentum of this would be 0.005 kilograms times 80 meters per second, 0.4 kilogram meters per second. We'll call that a positive quantity because we're shooting this to the right. Let's compare that to a tossed watermelon. Okay. Hey, our watermelon mass here, so I'll say the mass sub W, mass of the watermelon here. A good healthy watermelon has a mass of about 6 kilograms. That's around about 12 pounds, 12 to 13 pounds. Our friend here can toss it. We'll say again it's to the right. About walking speed, that's about 3 miles per hour. So we'll say that's about 1.5 meters per second. Okay, so what's the momentum of that? 6 kilograms times 1.5 meters per second. Well, again, note that as being a positive value. That's about 9 kilogram meters per second. So just looking at these two values, which would be the harder to stop? Looks like the watermelon would be harder to stop because it has a greater momentum. Well, what about the paintball pellet? Well, it certainly has a much smaller momentum, but it's concentrated in a much smaller area, so it might hurt a lot more. There will be times that we may know momentum information, but we're looking for either mass or velocity. Give you a couple of examples. Hey, often police or CHP investigators will look at an accident scene and be able to determine the momentum of a car after a collision. They know what the mass of that car is, and they want to know what the speed is. Well, you have a relationship that our momentum is equal to mass times our velocity, but in this case we want to know our velocity is. Maybe our accident investigators want to know if our guy here is speeding, but because of the damage involved, they already know what that momentum was at the time of the collision. So accident investigators have found out that the damage is consistent with about 42,000 kilogram meters per second of momentum at the time of the collision. And for this fancy car, we've looked in some book and found that the mass of that is about 1,400 kilograms. Let's take a look and see if we can figure out the velocity. And so I can look at this as being our velocity is equal to my momentum divided by mass. Let's put in our numbers. 42,000 kilogram meters per second divided by our 1,400 kilograms tells us that our car was going about 30 meters per second, close to 60 miles an hour. If, let's say, we're in a 35 or 45 mile an hour zone, we know that our driver here was being a bit irresponsible. Astronomers speculate that our moon was formed when the Earth and another body collided several billion years ago. Studies on the amount of material removed and all that have given scientists a pretty good idea of what the momentum was of the object before the collision. Now, these aren't exact numbers, but they're good for practicing our calculations. So let's say we had something like a momentum before the object impacted the Earth was something like 2 million kilogram meters per second. Hey, because of orbital positions, the velocity of the Earth and the other object could be pretty well known, and it was determined that the velocity of the object that hit the Earth was somewhere around 8,000 meters per second. And what we'd like to know is, hey, what was the mass of that object that could have produced such a collision? Let's go ahead and do the numbers. We know that our momentum is mass times velocity, which means that we could also express this as mass is equal to our momentum divided by our velocity. Putting in our numbers, I have 2 million kilogram meters per second as our momentum before this collision. I know that the velocity was about 8,000 meters per second, giving us a mass of the object of about 250 kilograms. Again, these numbers were simplified for the calculation, but that's the type of calculation a scientist could go through to get an idea of what was the size of the object that ran into the Earth that created the moon. Can you now calculate the momentum? Momentum is equal to mass times velocity. Remember, there's a magnitude and a direction of each of the object in a system. And can you determine the momentum, mass, or velocity of an object given two of the other values? Okay, with that, hope this was helpful.